Good morning, everybody. How's everybody doing? All right. Okay. Everyone knows the email RFCs are crazy. This talk will, without doubt, convince you not to follow the RFC. I'll show you why predicting an email destination is highly complex. And I'll take you on a journey of ancient protocols, exotic encodings, access control bypasses, and even how I gained remote code execution from an RFC compliant email address. I'm a researcher at Postfix, probably best known for breaking the AngularJS sandbox multiple times, crafting creative XSS payload, and building the Postfix XSS cheat sheet. Have you ever had that, I need to code this right now idea? That unstoppable, I can build this itch that you can't quite scratch until it's done? That's me constantly. One of my favorite side projects was building a 3D room for my portfolio. My brain decided to make this harder for me as it often does. And I thought, why not do this without JavaScript? And I was hooked. I even took the day off work to build it. My missus was not thrilled. The result was a fully navigatable world made purely with HTML and CSS. You can walk around the 3D rooms, even open the creaky doors. The hardest part was making it work in Safari. And 5 years later, it still doesn't. Maybe you can relate. Somewhere between hacking and building, I also wrote a book called JavaScript for Hackers, sharing how I uncover weird and wonderful XSS vectors and those beautiful broken browser quirks that lead to security bugs. So first, I'm going to explain why email address parser discrepancies matter. Next, I'll cover the shaky foundations on which emails are built. The core of the talk will focus on parser discrepancies, including Unicode overflows, Encoded-word, and Punycode, all with real-world case studies. Then I'll share my methodology and tools for automating exploitation, followed by advice on defense. I'll conclude with the key takeaways, leaving around 5 or 10 minutes for questions. So this research all started when we realized that many websites use the domain part of the email address to infer the user's organization and apply access control. And even Cloudflare Zero Trust can be configured to use the email domain to protect your internal networks. For example, Slack will also automatically give you access to your company's Slack channel based upon your work email address. This makes email verification a critical security boundary. What could possibly go wrong? It's well known that URL parser discrepancies are critical, as they can lead to SSRF, path traversal, and other security issues. Using email domains for access control makes email address parser discrepancies critical too. Predicting which email it should be routed to should be simple, but it's actually ludicrously difficult, even for RFC-compliant addresses. So we've established why email parsing matters. Now let's explore why predicting the email destination is so challenging. Email addresses are built on a shaky foundation of RFCs designed many years ago. Validation is often performed copy and pasting from Stack Overflow, trying to follow the RFC. We've all done it. However, one mistake in the regular expression can bring everything crashing down. I'm not going to bore you with RFCs, but I will highlight the important ones for this talk. For instance, the characters before the @ symbol in an email address are called the local part. The RFC allows what is called the quoted local part. This enables you to use characters in the local part that aren't normally allowed by enclosing them with quotes. In this example shown, I show a quoted local part that uses the @ symbol as part of the address. The same RFC allows you to use a quoted pair which means one character preceded by a backslash. This enables you to use even the double quote and the backslash as part of the address, providing it is escaped. Characters enclosed in parentheses are treated as comments and can be placed anywhere within the address apart from the quoted local part. They are ignored when the email is actually delivered. So here are two email addresses. You might be wondering which one is valid, as this is the typical question asked in an email presentation. However, this is the wrong question for this talk. The question you should be asking is which email domain does it go to? You might expect both emails to go to example.com. But that's not what happens. They both go to psres.net. Remember how I mentioned that predicting the destination of an email is extremely challenging? This is just the tip of the iceberg. The first example works on Postfix, and the second one works on SendMail. If you are confused, you should be. A source route is a sequence of servers for which an email is sent before reaching its final destination. Servers in the chain are separated by commas, with the final destination marked by a colon before the recipient's full address. Another form of source routing is called the %hack. Now, despite its name, the actual character used is determined by the mailer. In this process, the email is initially sent to example.com, after which the % symbol is converted to an @ symbol, and the email is sent to psres.net. This can be repeated several times. Before email addresses existed, and even the internet, people used to exchange messages using the UUCP protocol, which stands for Unix to Unix Copy Protocol. UUCP is an early protocol that separates the local user and multiple hosts with an exclamation mark, creating what is known as the bang path. Unlike the standard format for email addresses today, the bang path lists the hosts from left to right with the destination user mailbox at the end. So going back to those original examples with all the special characters removed, the parentheses effectively remove the @ symbol and the domain, and without the domain part, Postfix treats the email as a source route, a % source route. Using a backslash and escaping the @ symbol has the same effect in SendMail, which treats the email as a UUCP address. Now, I've removed all those special characters, but they do go to a mailbox I have tested. So I've just removed all the characters for clarity so you can understand what's going on. Now, I wish I could tell you that I uncovered this behavior by analyzing thousands of lines of code, using a debugger, and stepping through the code flow in SendMail and Postfix. But that's not quite what happened. I noticed a redacted target was allowing all sorts of special characters in its regular expression. So I took all the special characters, pasted them in my email, and then expected it to fail. But instead, I checked the syslog on the box I was testing and noticed a difference. I was getting host unknown error in the delivery status notification. This was significant because it would suggest a different host was being used. Now, if you look at the error, you'll notice that the exclamation mark is missing. I didn't actually notice that at the time. So I started to remove characters, resend the email, to see if I got the same error message. I narrowed it down to the exclamation mark and thus discovered the UUCP behavior. This was absolutely bonkers. By sheer luck, the characters I pasted into the email ended with a backslash, which escaped the @ symbol, and the exclamation mark was treating the address as a UUCP address. I then wrote a fuzzer and found the other behavior with source routes in Postfix. So this was pivotal for my research, because these findings gave me confidence that there are tons of bugs out there, so I began to look for more. So before we move on to the next main topic, I want to take a quick detour into some bonus material that I've prepared. I discovered a genuine SMTP injection vulnerability involving SMTP parameters on Postfix on a redacted target, along with some intriguing UUCP-based vectors and some unexpected source root behavior. All these examples show how legacy features can still surface in modern environments, often in ways that developers don't anticipate. To understand the next set of slides, let's quickly recap on how an email is sent at the SMTP level. When a message is delivered, the mail client and the SMTP server perform a short command-based conversation. The part that matters for this talk is the receipt to command, which specifies the actual recipient address for delivery. You'll notice that the receipt to command is enclosed in angle brackets. On the next slide, we're going to show how to abuse these brackets to change the destination address. In the RFC, there are optional SMTP parameters. I analyzed the Postfix source code with a Portswigger colleague, and I discovered that you can use these parameters to remove the domain part of the email address. I found this parsing bug on a real target, but the application in question didn't use the email domain for access control. The attack works by escaping the backslash to break out of the quoted local part, which confuses the email validation. Then you can use the greater than to end the receipt to command, followed by a space, and then the original recipient parameter to hide the rest of the address. The semicolon is required for this to work. So the first one is my email address. The backslash confuses the validation. The second one is the actual SMTP conversation. So you can see I'm stuffing the rest of the address in that parameter, and that results in an email to psres.net. I found that Postfix also supports UUCP2, and I was quite surprised at this parsing behavior. If you escape a double quote inside a dangling comment, Postfix as well treats it as a UUCP style address, resulting in an email sent to psres.net, not example.com. In this final example, Postfix interprets the address as a source root, even when written with a perfectly valid RFC compliant address with square bracket syntax. So you might expect this to go to localhost, but it actually goes to psres.net. So the main problems I had to solve with this research was generating blocked characters, since many web applications block multiple @ symbols. This following section focuses on Unicode overflows, which enable you to create ASCII characters from higher Unicode characters. The PHP char function is a good example of how Unicode overflows can occur. The function generates a character from an integer code point. Here's an illustration on how the algorithm works for this function. It loops through the code point while it's less than 0, continually adding 256 until it's non-negative. Because why not? This is PHP after all. It uses the mod operation to ensure the byte value is always in the range of 0 to 255. If you introduce a Unicode character whose code point is larger than 255, it will be truncated into this range. Note that Unicode overflows, they're not just specific to PHP, but PHP provides a really good example. Generating a Unicode overflow in JavaScript is quite simple, using the fromCodePoint method. First, you pass the number that you want to cause the overflow, such as OX100, which is 256 in decimal. Next, you provide the actual hex number to generate the actual character that you want, for example, OX40, which is the @ symbol. The fromCodePoint method will then generate a Unicode character, and when that character is transformed to fit within 255 by a system that doesn't support higher Unicode characters, it will produce the ASCII character specified by the hex number. So in other words, the first number causes the overflow, and the second one generates an @ symbol when it's fit into the restrictions. So I hunted for real-world Unicode overflows and found a target that altered characters within the SMTP conversation of the mailer. The application blocked the backslash, but I used blocked the backslash within the quoted local part, but I bypassed the validation using Unicode overflows. That enabled me to escape characters and break out of the quoted local part. Despite this, when using an encoded @ symbol, the email wasn't sent, suggesting there was double validation going on, once in the application and once before sending. So although I didn't manage to exploit this particular target, the key takeaway is that Unicode overflows can bypass validation and smuggle characters into the SMTP conversation. So although I didn't exploit Unicode overflows with this particular example, later on in the presentation, I will use an advanced Unicode overflow that does. So Unicode overflows were great, but I needed more methods to generate block characters. So I took a deep dive into the glorious RFCs, looking for gold, and I found it. This next section is about encoded-word. I discovered this when trying to find ways of generating the @ symbol without the Unicode overflow. Encoded-word is specified in RFC 2047 and allows the inclusion of Unicode characters using encoded data. And here is how encoded-word works. It's beautiful, right? First, the equal sign and question marks begin the encoded word. Next, comes the character encoding, which in this case is UTF-8. The question marks act as separators between the char set and the encoding type. Inside those separators is the encoding type, in this case, Q encoding. After that, you have the encoded data. Each character has an equals prefix followed by the hex value. For instance, equals 41 represents the uppercase character A. Finally, a question mark and equal sign end the encoded word. And once the email is parsed by the email parsing library, the encoded characters are decoded, and the encoded word meta characters are removed, and the decoded address is shown below. Quite surprising, I'm sure you'll agree. To probe for encoded word, you should make 2 requests with 2 char sets. The reason for this is that many email parsing libraries support different char sets. So when probing, you should use lowercase characters in case the site rejects or transforms to lowercase. I was initially using X as the char set to reduce the size of the probe. However, some systems will reject unknown char sets, and they would fail. So it's better to use these 2 probes and then follow up with a char set of X to see if it works. If successful, in each case, it should send an email to the addresses displayed. In a real probe, you would use something like the collaborator with your collaborator payload. I've highlighted the encoded and decoded texts in red. For example, equals 61 is a hex-encoded lowercase character A. So we've covered how encoded word works. Now let's look at some real-world case studies. The following case studies all use the Ruby Mail library, which has over 508 million downloads. At the time of testing, the version was 2.8.1, and this library is used by many popular Ruby applications, including GitHub, Zendesk, GitLab, and BugCrowd. For my first case study, I'm going to show you how I exploited GitLab Enterprise. I love this vector because it's so simple. First, I use a char set of X because GitLab Enterprise didn't care or validate it. Next, I used an encoded @ symbol, so that's equals 40. After that, I add an underscore character. Now, an underscore character represents a space in encoded word, as well as equals 20. As a result, the email is split in half, and the message is sent to psres.net, while GitLab Enterprise still believes the domain is example.com. So what was the impact? Well, I could verify email addresses on domains I don't control. This means I could have gained access to GitLab enterprise servers that use domain-based registration restrictions. So in other words, I could use an email address to get your source code. GitLab is also an IDP, and I exploited their email verification too. For this, for the slide, I used a char set of X, but in a real attack, you would supply a valid char set. I couldn't fit it all on in the slide, but you would use an ISO char set to attack those, because GitLab blocks unknown char sets. Next, I include an encoded @ symbol again, which is equals 40. After that, I add a greater than character, which is equals 3e. Then I append a space after that, equals 20. And the result is the email is delivered to psres.net, while GitLab online application still believes the domain is example.com. Using this bug, I could bypass domain-based access controls on websites that use GitLab as an IDP. I had verified email addresses from @microsoft.com, @gitlab.com, or any other domain I like, which was quite fun. It was like a trophy. In this next technique, I'm going to show you a more complex attack that worked on Zendesk and uses the quoted local part with encoded quotes. So first, we begin the quoted local part with the double quote. Next, we begin with the Q-encoded double quote, so this is equals 22. Then we include an encoded @ symbol, which is equals 40. After that, we add the greater than character, which is equals 3e, and then the null character this time, which causes the mailer to ignore everything that follows. And because of the quirks of the mailer and Zendesk validation, an encoded less than character was required, which is equals 3c. This seems to get stripped out and leaves an encoded double quote, which is equals 22. We then close the quoted local part, and the result is that email is sent to the following address with all the quotes removed. So when testing this system, it felt like there were multiple layers of Q encoding going on. So like you can see the double encoded data is decoded. So they must have been parsing this email multiple times. The impact of this attack was attackers could verify email addresses on domains they don't control, which means you could have gained access to Zendesk email domain protected support centers. Surprisingly, GitHub was also vulnerable to the greater than and null attack. First, I created an encoded @ symbol, again equals 40. Next, I added an encoded greater than character, equals 3e. And then I include a null this time, and then the rest of the address is ignored, which results in the following email. So yeah, these online versions like GitHub and GitLab Enterprise required a combination of 2 characters to split their email. Using this technique, I was able to verify any domain I liked, and my GitHub account had emails from @mozilla.com, GitHub.com, and Microsoft.com. So that was quite fun. I bet I could do some damage with that. Obviously, I didn't. So by spoofing domains on GitHub.com, I could verify email domains on ones that I don't control. This enabled me to bypass domain-based access control restrictions that use GitHub as an identity provider. For example, I could even penetrate internal networks protected by Cloudflare Zero Trust if they were configured to use GitHub domain validation. This screenshot shows Cloudflare Zero Trust trusting email domains from github.com. And since I could spoof and verify any domain I liked, this vulnerability affected all Cloudflare Zero Trust instances that used email domain validation. While testing multiple Ruby systems, I found you could also use a base64 email address. Because why not? Clearly, this is something we all desperately need, and what could possibly go wrong? In this example, the B indicates base64 encoded word, Then comes the base64 encoded data, foobar, and ultimately results in the following email. Now, I've encoded foobar here, but you can encode anything you like, including spaces and the @ symbol. Anyone remember this? If you're not into security, yeah, one there. So, yeah, this is a UTF-7 encoded script alert 1. This used to work on the glorious Internet Explorer. Awesome vector. You might be wondering why I'm mentioning this. Surely email parsing libraries won't allow a UTF-7 encoded char set. Of course they do. This is a UTF encoded foobar. The char set is decoded and the message is sent to the following address. And yes, if you're wondering, or maybe it's just me, you can combine UTF-7 and base64 encoded data. This is crazy. In this example, the email address is base64 encoded and a UTF-7 char set. First, the email parser decodes the base64 data. Then it decodes the UTF-7 char set. Finally, the email is decoded and delivered to the following address. Then I wondered, what if you mixed UTF-7 and Q encoding? Surely they won't allow that. Here I take the letter A and replace it with equals 41. That value is decoded, which produces a UTF-7 encoded foobar. The email passes through both layers of encoding before reaching its final destination. Now, by this point, you might be questioning the wisdom of following the RFC, especially when I tell you that this works in the domain part as well when testing the Ruby mail library. I know what you're thinking. No website will ever support a UTF-7 encoded email address, right? But this did work on a small source code hosting website, GitHub. So I was hunting for Encoded-word outside of Ruby, and I found that PHP Mailer supports Encoded-word within the name of the recipient. So I tried exploiting WordPress and other applications, but this requirement of needing angle brackets made email exploitation difficult. Still, I bet there are vulnerable systems out there if they reflect the decoded name. So you might try this technique to get XSS, for example, on applications if they reflect a decoded name value. So we've explored how you can manipulate email parsing to sidestep access controls. But let's take this a little bit further. What if an email address could be weaponized to gain remote code execution? In this next section, I'll cover Punycode attacks and how I exploited Joomla with an advanced Unicode overflow. So remember the PHP example I shared earlier in the presentation? I'm using an advanced Unicode overflow that takes advantage of the fact that you can have minus values and generate characters. Punycode is a way to represent Unicode characters in the current DNS system. Punycode always starts with XN and followed by 2 hyphens. The algorithm converts a sequence of Unicode characters into a representation that utilizes only alphanumeric characters and hyphens. For example, the domain muchen is encoded with the following Punycode sequence in red. So I hope I pronounced that right. The very nature of how Punycode works makes it really difficult to test because changing one character can change the entire output and even the character position. And this is just how the algorithm works. What we want to do is generate some malicious characters that when decoded, it produces like XSS, but doing so is a big challenge. In these examples, you can see the Unicode character is changing its position every time I change the number. So you can see the Unicode character is moving to the right, and all I'm doing is just changing one number. So after reading about Punycode, I followed a link to an online Punycode converter, and I began to experiment. The converter used the IDN PHP library. So I first tried adding zeros to the beginning of a Punycode address to convert it into ASCII characters. So you can see what I was trying to do here. I initially generated a comma, which was so surprising I doubted my eyes. So encouraged by this, I experimented further and managed to produce the @ symbol. This was exciting for me. After searching GitHub, I found an interesting target using the library, Joomla. This was great because if I got XSS, then I would have RCE. So doing some source code analysis, I noticed they were escaping the email address of the user before it was Punycode and decoded. So what this means is, if I could produce some malformed Punycode that produces HTML, I could get XSS, but it wouldn't be that easy. So it sounds simple, right? Just give the decoder some malformed Punycode and generate some HTML. But remember how the algorithm works. Any change in the character can result in a completely different output. So I thought this is a job for a fuzzer. So I wrote a fuzzer to generate malformed Punycode, and the results were interesting. I found many ways to generate different characters. So you can see what I was trying to do here. I'm trying to generate an SVG tag with a slash. And if you notice the Punycode addresses, they're all different, but they still produce the same tag. So this is what I was trying to exploit. So I started generating millions of different character combinations. I managed to construct partial XSS vectors, but I encountered several issues. I could only generate 2 ASCII characters by using more than one Punycode subdomain. This limitation arose from the specific workings of the Punycode algorithm, PHP, and the quirky, buggy PHP IDN library. As you can see in these examples, I was really close, but these problems made exploiting Joomla very difficult. I concluded that XSS was not feasible because although I was able to generate a single quoted HTML attribute, it required an underscore character. Joomla, however, does not permit underscore characters in the domain part of an email address. So was that the end of the story? Not quite. I thought about this for a while, and I worked out if you use a single Punycode subdomain, you can generate any opening tag. Eventually, after a lot of testing, I concluded that the only exploitable vector was an opening style tag. Here, I use malformed Punycode to construct it. So it looks like a test string, right? It looks like literally I've made it up, 3, 2, 1. But it actually is malformed Punycode that when used with this buggy PHP IDN library, it converts it into a style tag using a Unicode overflow. And I could do an entire presentation on how that works. Because basically what happens is all these characters get interacted with each other, produces a minus value, then PHP adds 256 until it's non-negative, and then produces the character. It's really crazy stuff. So this produced a style tag. Helpfully, the rest of the pre-existing Joomla HTML code would add the space for me and the closing angle bracket, because why not? This is HTML after all. So all I've got is a less than character and the style, and the existing TD tag will complete that tag for me, and HTML is just fine with that. So I would need 2 accounts. The first would create the style tag with the malformed Punycode, as I've previously demonstrated. And the second account contains the actual CSS payload inside the name field, and that would import a malicious style sheet. The first account name starts with A, and the second account name starts with X. This is to ensure the style injection occurs first, and then the second account uses the import. Note, I'm using curly braces to treat all the HTML that occurs before the import as an invalid CSS selector, because why not? This is CSS after all. All the HTML before is treated as an invalid CSS selector, and CSS is fine with that. So the first step is to register 2 accounts. One with the malicious Punycode, and the second containing the embedded CSS payload in the name. Note, the administrator does not even need to approve these accounts. So the first account, the malicious Punycode is in the email, and the second account, the malicious import statement, is in the name field. So the attacker uses import chaining and a custom node-based CSS exfiltrator I wrote to quickly exfiltrate the CSRF token from the admin when they visit the user list page. So the admin logs on, visits the user list page, and because I've got persistent CSS injection, it will exfiltrate the token from the admin. Using the exfiltrated token, the attacker instantly knows that the admin has visited the page. So I use the exfiltrated server, the CSS exfiltrator server, to give the admin a URL. The admin clicks on the URL, and then the CSRF token is used by the exfiltrating server and then performs a CSRF attack that modifies an admin template, and then that gets RCE. Now, I'm going to attempt to live demo this. The victim browser, the admin, will be on the left, and the attacker's browser will be on the right. The terminal will contain the exfiltrator server. So let's pray to the demo gods. Please be kind. Can everybody see? Yep. Okay. So on the left, we've got the admin browser. So this is the administrator. The right is the attacker. So the first step for the attacker is to inject the malformed Punycode. So I'm going to pre-fill this because I'm sure you don't want to see me type it all. So the Punycode is in the email address, so you can see the style 321 in there. So we register that. Now we get an error. It's not an error. It's just the fact that I've not configured SMTP on the Joomla instance. So now the attacker then pre-fills the name field. So you can see we've got the import statement in the name field, and we register the second account. Now, we've got, this is the, let me reduce this a bit. So the attacker then runs the exfiltrator server. So this is the Node.js server that's running to exfiltrate the token. Then the admin logs on, visits the user list page. You can see the token being exfiltrated. So then the attacker knows this. So we go, hello admin, hi there, how are you doing? I'm doing great, thanks, how about you? Or, you know, just living the dream. Can I exploit you now? Yeah, of course you can. Click on the link. So Joomla is now backdoored. So now the attacker, all they have to do is visit the backdoor. So we visit the backdoor, and then I'm catching etc. password, and we've got RCE. Phew, thank you, demo gods. So when conducting this email parsing research, I found it useful to use the following methodology: probe, observe, encode, exploit. First, probe for encoded-word. Observe the decoded email to confirm that it's supported. Then encode the various characters and observe how they're decoded. Then follow up with an exploit that abuses those characters. This methodology can also be applied to Punycode. So here's how I do it. This is like a way of seeing an email system is vulnerable. So first you can see I'm encoding equals 61, equals 62, equals 63, which is an encoded ABC. So first I probe for that. I observe how it's decoded, so that results in ABC. Then I follow up with a quoted local part and try and encode the @ symbol and observe, oh, the @ symbol is decoded. This is really useful. And then I follow up with an exploit because I know all these characters are being decoded. I use the underscore as a space to split the email in half, and then you've got an exploit. So you can apply this methodology to the various things that I've shown in this presentation. I've added new tags to HackVerter, our free open source Burp Suite extension, to help with the creation of Unicode overflow and encoded-word attacks. I've also developed a set of turbo-intruded scripts to explore how different parsers handle encoded word, including edge cases like null bytes or spaces. These scripts are available on our GitHub repository, and we've also updated burp intruder word list to support this work. Finally, I've built a Punycode fuzzer that mutates placeholders within Punycode addresses using random characters, digits, and white space to help surface malformed or unexpected variants. If you don't have a copy of burp, that's fine. You can use the free online version of Hackverter to reproduce some of the attacks in this presentation. You can use simple tags to construct encoded word and base64 encoded emails. It's available on hackverter.co.uk. To defend against email splitting attacks, make sure you filter out or disable encoded word. It's a really bad idea to have it enabled. Always verify email addresses before using them, and even when received from an SSO provider. After validating an email address, do not use the domain as the sole means of authorization. As we've seen, that's a really bad idea. A few blog posts and slides were inspirational when conducting this research. I really recommend you read each one because they contain really useful information. The import chaining technique I used to exfiltrate the token is from Pet Villa and Donut. The three takeaways I want to leave you with are: valid email addresses can trigger major parser discrepancies. Even addresses that end in @example.com might go elsewhere. As a result, it's never safe to use email domains for access control enforcement. We've created a Web Security Academy lab, which is totally free, and you can use this to practice your email splitting skills, as well as a Docker file with the vulnerable Joomla installation. So if you want to replicate the Joomla flow that I demonstrated, you can do so using Docker. You can get all the links and download all the materials for this presentation at our GitHub repository. And if you want to explore the 3D rooms I built entirely with HTML and CSS, no JavaScript, then please visit my site. And if you'd like to continue your journey into creative web hacking, my book, JavaScript for Hackers, is available on Leanpub and Amazon. Thank you so much. Hope you enjoyed the presentation. Thank you. Any questions? Sure.
Thanks for the presentation. That was fun. Did you report back to GitHub, GitLab, and Joomla about the specs? And if you did,
Yes.
fixed?
Yeah, I got bounties for them, and yeah, they're all fixed. Yeah. Yeah, sure.
You use PHP and you use Ruby.
Yeah.
Have you looked at other ecosystems to see how extensive this is?
I looked at multiple systems. I had test cases on various different platforms like Java, for example, and Node.js. There are quite a lot of systems to test, so I couldn't test them all. So what I tended to do was focus on the ones that I could easily exploit, which was the ones I demonstrated. But yeah, this goes across. This is in the RFCs, and anywhere where you parse an email and then you send the parsed email, you send the email to the parsed email, you're in danger because this is in the RFCs. So a lot of systems will be vulnerable to this. Any other questions? All right, then. Thank you. Cheers.